Hey there, STEM Chemistry. This is Miss Ruark. We're in podcast 1.5, where we're going to talk about a little bit more about the atomic theory. We're going to talk about electron configuration and quantum numbers and what all that means to us. This might go a little fast, so if at any point you need to, just pause and then come back. All right, so we need some more history. Let's do some more history. Okay, we've already talked about Democritus, and we said that this guy was a very old Greek philosopher, and he was the first person to say that atoms do exist, and he came up with the word atomos, which is the Greek word for atoms. And then after him, it was probably about 200 years later, an English school teacher by the name of John Dalton came up with the atomic theory. Now, he based this theory on work that had been done between the time of Democritus and he started doing his theory. But in his theory, he said that all matter is made of atoms, which are indivisible and indestructible. He also said that all atoms of a given element are similar in mass and properties. He said that compounds are formed by combinations of two or more different kinds of atoms, and in a chemical reaction, the only thing that's happening is a rearrangement of atoms. Okay, so this is his theory based on different research and work that was done by different scientists before him. All right, well, we know that J.J. Thomson did the cathode ray tube experiments. He discovered the electron, and he came up with the plum pudding model of the atom, which was later discredited by Ernest Rutherford, who did the gold foil experiments and discovered the nucleus, and that inside the nucleus it was dense and it was small and it had positive charges inside of it, which we call protons. And then James Chadwick came after him, and he discovered the neutron. Well, then we have a gentleman by the name of Max Planck, and Max Planck was a German physicist, and he is the one who came up with this theory that radiation emitted from or given off from atoms is not shown continuously in a continuous spectrum, but it's shown in small, discrete packages, which we call quanta. Yeah. Ooh, we're getting into some good stuff here. All right. After him, Albert Einstein came along with the photoelectric effect. And with this photoelectric effect, he said that there's an emission of electrons by metal surface that's being irradiated by light or more energetic photons. And he also said that the kinetic energy of this kinetic energy is dependent on the frequency of the radiation, but not the intensity of the radiation. Well, right after him came along Niels Bohr, which we talked about in the last podcast. And Niels Bohr came up with this line spectrum idea and the model, and his came up with three assumptions that said electrons are only shown in stationary states, which are those orbits. These orbits or stationary states are those which the angular momentum or the spin, the rotational inertia of an electron is a whole number. And then he used Newton's laws to calculate the orbit of an electron around the nucleus. Well, a lot of his stuff is still used today, and that's why we talk about him so much. Well, after him was a gentleman by the name of de Broglie, and his research came up. He said that matter has wave-particle duality, which means that matter can behave as a wave, but it also is a particle. It's a small little particle that's going to behave as a wave. All right, and after him was a guy by the name of Erwin Schrödinger. He was an Austrian physicist who did a lot of work with this wave theory, and he came up with the wave theory of matter, and he is the one who started the work on quantum mechanics. Yay! Let's see, and I had electron here for a reason, and I can't remember why. I don't know. Let's see. Checking my notes. Sorry. Oh, yeah, that's right. All right. He's also the one that said, hey, guess what? Bohr was kind of right in the fact that the electrons are outside and they move around, but they aren't in distinct set orbits. They are located in clouds or orbitals, which would be 3D regions of space. Okay, so what is a quantum number? So quantum numbers are something that we use in order to tell or describe the probable location and the behavior of these electrons. Okay, so there are four main quantum numbers that we are going to be concerned with, and the first one is the principal quantum number. The symbol for the principal quantum number is a lowercase n. We've already seen that, right? We said that n is equal to the energy level of an electron. Well, guess what? That's what this shows here. It's the energy state, and it also tells us the probable distance from the nucleus, and it's always going to be in integers 1, 2, 3, 4, 5, 6, 7, and it keeps going. Okay, this principal quantum number, as the n increases, as the number, the energy level increases, the amount of energy increases, and it's further from the nucleus. Okay, so increase in n, increase in energy, increase in distance from the nucleus. All right. The second quantum number that we would show is the angular quantum number. And the symbol for that is usually a lowercase cursive L, but I can't get it to do cursive. It does italics. Okay. And the angular quantum number is going to show us the shape of the electron cloud or the orbital. And the numbers that we can have for this, and remember these are quantum numbers, so there are four numbers that we're going to show all of these things with, no letters. All right, and the shape of the electron cloud, it can have a value from 0 to n-1. So if it's in the first energy level, your angular quantum number is going to be 0 because n-1 is 0, right? Okay, if it's in a if it's in energy level 2, what's 2 minus 1? 1. So your angular quantum number would be 1. Okay. And it's based on the shapes of the orbitals. So here are a picture of your orbitals. You have four different orbitals. You have your s orbital, which stands for spherical, and those are all going to have a L value of 0. Here, those are all here. Okay, here you have your p orbitals, and those will all have a quantum or a angular quantum number of 1. Here, let's see if I can change my color. Let's go yellow. All right. Here you have your d sublevel, and those will all have an angular quantum number of 2. And then these down here all have, these are the f sublevel, and they are orbital, and they all have a quantum number equal to 3. Okay, so and we could keep going. Okay, we could keep going if we have more orbitals past this. Okay, so S stands for spherical. They're all round in shape. Spherical meaning three-dimensional in shape. So you have not only your, let me change to another color now because it needs to be darker. Okay, you not only have your X and your Y axis, but you also have your Z axis, 3 dimensions in space. And your Z is shown this way, but actually it's coming towards you and going into the wall behind or past the computer screen. Okay. Your P sublevel is it looks kind of like this. I say it's dumbbell shaped. Looks like a bunch of dumb shells. You could call them petals if you wanted to. Okay, and then your D is going to be an extension of this. It just has more petals in there. Starting to make a flower, right? And then your F, I always call them F for funky, but you know, you can call them what you want. But it's just more petals thrown in there. Okay, and remember they're coming out towards you and going into the wall behind, in front of you. Okay, then our next is our magnetic quantum number. We label that M, and it can have a negative L value, negative L, to a positive L value. So it can be anywhere between whatever your quantum number is to the negative quantum number. So for S, if your value for L is 0, of course your quantum number, your magnetic, will be 0. If your quantum, or if your angular momentum number is 1, you could have values from -1, 0, or positive 1. Right? For your D sublevel, since it's a 2, you can have -2, -1, 0, 1, or 2. And then for your F, you can have -3, -2, -1, 0, 1, 2, and 3. Whew. I know quantum numbers. All right, and then the last one we have is our spin quantum number, which can be symbolized as M sub S or just plain S. I've seen it both ways. And this tells us the angular momentum or the rotational inertia. Right? Inertia is the tendency of something to keep moving if it's already moving unless acted upon, or to stay at rest. Right? So angular momentum is how it's spinning or going round and round and round in circles. Due to the orbital motion of the electron, it can only have two values. It can have a -1/2 or a +1/2. And these are given based on the clockwise or counterclockwise motion of the electrons. All right, and then electron configuration. So electron configuration is just another way to show the probable location of an electron in an atom. Right? It uses numbers and letters, so you actually have numbers and letters in here, not just numbers, yeah. And it's based off of the periodic table. Okay, now the periodic table is broken up into periods, 1, 2, 3, 4, 5, 6, 7. And the periods are these energy levels, right? N equals 1, 2, 3, 4, 5, 6, 7. Here are your energy levels. And then I just showed you that this would be your S sublevel or orbital. This would be your D, sorry, not your D, your P. Your D would be here in what I like to refer to as the swimming pool. And then these two down here are your F orbitals. Right? And then all you're doing is you're showing if it was, let's say we had to do the electron configuration for helium, well, we would say that helium is in the first energy level. It is, I know it's over here, but it's not technically a P. It's over here because it behaves like a noble gas, but it should be here when we're looking at electron configuration. So we would say it's in the 1s, and there are 2 electrons located in it. Don't worry, if you don't get this, we're going to practice it in class. All right, so let's say that we were looking for, how about selenium? Okay, so selenium is all the way here in the 4th energy level. It is in the p orbital, right? And it is the 1, 2, 3, 4th one in. So in order to write 4p4, that would just say that's where the last electron would probably be located. But for electron configuration, we have to show every single one. So we have to start at the beginning. Yep, got to start at the top. Read the periodic table like a book. And we fill in every single energy level, every single sublevel or orbital, and then every single electron. So we would start here and say 1s2, 2s2, because we're filling in 1s with both electrons. 2s, we're going to fill in both of those. This is still 2p, and we have 6 electrons there. 3s with 2 electrons. 3p with 6 electrons. 4s with 2 electrons. Okay, now you get here and you're like, oh, it's going to be 4D. Well, actually, this one is N-1, which means that, and I'll talk to you about it in class, it overlaps. So this is actually 3. It's still part of this 3rd energy level. Oh, yeah, this is when it gets really fun. All right, and this is 3D. And there are 10 boxes here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're right back at 4 again, so 4p4. And then just for some more fun down here, these two are actually overlapping even more, so these would be N-2. Now, if I have just made your head spin, it's okay. If your mind is blown, it's okay, because we're going to practice this when you get to class, and we will make more sense of it. So as you're going through this, if you have to watch it again, write down questions that you might have, put stars next to things that you're like, I just don't get that, because I will make sense of it when you get to class. All right? Oh, and there's the electron configuration. Okay, and I'll see you in class.